Okay, so I wanted to do one more video with some examples before going on to um, power series. And so let's look at this. I've got a few examples down here, none of which are particularly easy. So let's see if we can figure out how we want to approach them. Now, what are the tests we have? We know a few series. Let's write down what we know. We know geometric series, right? And P series. We have the integral test. We have the comparison test and the comparison and the limit comparison test, right? And then we have the ratio test, well, the alternating series test. The ratio test and the root test. And these are the things we have to work with to tell if a series converges. So let's look at this first one. This first one here, it's got to be, well, first off, it's got positive, it doesn't have all positive terms because sine 2n might sometimes be negative. So we can't use a test directly that compares it to something with all positive terms, but we can look at the absolute value of that. The absolute value of the terms here, sine 2n over 1 plus 1 plus 1.1 to the n. Well, that's going to be less than or equal to 1 because the absolute value, sine is always less than or equal to 1, right? So that's going to be less than or equal to 1 plus 1.1 to the n. Now, 1 plus 1.1 to the n is, well, that's less than 1 over 1.1 to the n. And this is a geometric series, right? 1.1 to the n is 11/10 to the n, so this is 10/11 to the n. So the series with these terms converge. This thing here converges because it's a geometric series, r equal to 10 over 11. So that means this thing here converges, the series with these terms here converges. And therefore, this converges absolutely, and therefore it converges conditionally. It converges in general. So the absolute value of this converges, and therefore it converges. So sometimes you got to go through a few things to get there. Now this one, well, it's an alternating series. We can tell if it converges by determining if the terms go to 0. So let's check that first, and let's see if we can tell if it converges absolutely. Because the alternating series test only tells us if it converges or not. If it doesn't, then we've got nothing to worry about. So let's see, I'm going to use L'Hopital's rule on this limit. And we get 1 over 2 square root n divided by 1 over n, which is equal to, oops, sorry, that's the limit. Limit n goes to infinity. I give you guys extra credit for catching when I leave that off, right? N goes to infinity of n over 2 square root of n, which is equal to the limit n goes to infinity of square root 1/2 square root of n, which of course that goes to infinity, not 0, so this diverges. So it doesn't converge absolutely, obviously it just diverges. There's nothing more to say about that one. So good thing we didn't try too many other tests on that first. Okay, so now this one, well, the terms are positive, right? But this is probably not a good one for the integral test because x factorial doesn't really make sense in general. It's not a good one for the comparison test or the limit comparison test because, well, we don't really have a good thing to compare it to. So we're going to try the ratio test, and hopefully the ratio test, that limit gives us something that we can work with. So let's look at the limit. So we're going to use the ratio test. I'm going to look at the limit as n goes to infinity. I don't need to worry about absolute values since it's positive. So 2 times n plus 1, that thing factorial, over n plus 1 factorial, that thing squared. Whew. Takes a lot to write there, doesn't it? Over 2n factorial over n factorial squared. So rearranging that, that's going to be the limit as n goes to infinity of n factorial squared times 2n plus 2 factorial over n plus 1 factorial squared times 2n factorial. Okay, so we can simplify. Remember, n plus 1 factorial is n plus 1 times n factorial. So we can cancel an n factorial from each of those. There's a squared, but we can cancel it from each of them. So we get, in the denominator, we're going to get an n plus 1 times an n plus 1, an n plus 1 squared. And notice, well, let's just point this out. 2n plus 2 factorial is equal to 2n plus 2 times 2n plus 1 times 2n factorial, right? So we can cancel a 2n factorial there as well. So we've got, this is going to leave us with an n plus 1 squared in the denominator, and 2n plus 2 times 2n plus 1 in the numerator. And so what do we have here? We have, well, this is a rational function. We can tell what the limit is. It's degree 2 polynomial on the top and the bottom. The leading coefficient of the numerator is 4, and of the denominator is 1. So that limit is 4, which is bigger than 1. So this diverges by the ratio test. And I'll stop there. Okay. Bye. Next, we're on to power series.